lucky to have Gert de Cooman here with Jasper. I mean, I very much appreciate everybody being here. Like Teddy, most things that you think you might want to write about, you probably should check to make sure that it hasn't already done it.
I checked.
Yeah. But today he's going to tell us a little bit about randomness and precision scoring. So thank you, Gert.
Thank you, Jason. I'm going to try to be as brief as I can. I'm going to talk about randomness and imprecision. And I have definite ideas about those two things. My ideas are fully baked, perhaps not too crisp, but at least fully baked. Then I'm going to try and say a few things about scoring, and those ideas are only half baked. So it's just things that I'm going to throw at you, flip a few ideas around. I have to say, probably need to make sure that no pizza was harmed, nor shamelessly exploited in the making of this presentation. So I want to get that out of the way. Okay. So I have to also say that this has been a close collaboration between myself and Jasper and Floris, who is a member of our team, who's also working on randomness. And it's also resulted from discussions with Philip, David, Volodya, Glenn Schaefer, and Teddy Zeirenfeld, who you see there holding up his prime example of independence in a beautiful construction. Anyway, let's start with a bit of history. What you're looking at here is a probability tree. It is probably the first probability tree that was drawn in the history of probability. It was drawn in the late 1650s, close to 1660, by Christian Huygens. And he drew it as a result of learning about the conversation between Fermat and Pascal on the problem of points. And it actually summarizes his ideas on a specific sub-problem, a special problem in that problem of points. So let me explain a bit what's going on. We have two players, player A and player B, and they will play a game that consists of successive rounds. And in each round, player A has a certain probability of winning the round, that is P, and player Q has another probability, has a probability of winning the round, that is Q, or 1 minus P, of course. So that they have this part of winning a round, and when you win a round, you get a token. Yeah. And so you can play successive rounds of the game, and then you accumulate tokens as you go along. And the deal here is that the game will stop as soon as the difference between the two players, as far as the number of tokens is concerned, is 2. So it will stop after the difference has reached 2. So they start with the same number of tokens, 0 each, and then the game starts. Yeah. And the idea is that the X here on the slide is the thing that we're looking for. And there's actually the price that that player A should be willing to give in order to participate in this game. So the price for him that is equivalent to playing the game and getting the rewards. It's because at the end, he will get, the player who wins, who has 2 tokens more than the other one, will get 2 euros or 2 florins or whatever it was in those days, dollars probably. And then in other situations he will get either nothing or the other player will get something. So that is what happens. So you may have to pay 2 to the other player. So that is happened. So in the conversation between Pascal and Fermat, they deal with a more complicated version of this problem. And they come up with a solution, and actually each of them comes up with a different solution. And much of the conversation deals with trying to come to terms with the fact that they don't believe that the other's solution is correct, and then converging on the idea that perhaps they've hit on the same idea, although different aspects of it. And I'm going to try to detail this a bit. So in Pascal's approach, what happens is I've drawn the probability tree here and the number of tokens also. So here 0, 0 tokens. If A wins, he gets with probability B, he gets 1 token. Otherwise, B gets a token. And then here you get 2 tokens, 1, 1 token, 1, 1 token, and 0, 2 tokens. So that is the situation that you have. And of course, here the game stops because there's a difference of 2 tokens, and the player gets 2. Here the game stops, and the other player gets 2, or he loses, or player A loses 2. And here, what happens actually is that you have the same number of tokens. So essentially, in the same situation as here, because you have the same situation, and this means that the game will just repeat itself all over again. So you can just copy the entire tree back here. You get an exact copy of that tree. So that is what happens. So how does Pascal solve this problem? He starts by adding prices to each of the nodes. So he says, okay, here player A will get 2, here he will lose 2, and here he gets what I'm looking for, namely X, because this is the beginning of the tree. So here I get X, and here I get X. And also here, of course, I get X. So now, and now the important step is he then places himself here in this part of the tree, and he looks forward and says, okay, what I see here is something that is uncertain. It's either 2 or X. What can I put here that is equivalent, that is fixed, that is not uncertain, that is fixed, but that is equivalent to what is here? That I find that to me is the same thing as this uncertain reward that I get. And of course, he then argues that this should be what we now call expectation. Yeah. So he gets twice B plus Q times X. And here you get the same thing. You place yourself here and say, okay, what I get is B times X plus minus 2 times the Q. And then he moves back, goes to this situation, and then says, okay, in this situation, I have 2 things that are now 2 rewards that are uncertain. And I'm just going to ask myself what in this situation is equivalent to these 2 uncertain rewards. Do the calculations. Again, calculate it, find this. And then, of course, this must be equal to this. And then you can solve for X, and you find what you needed to find. Yeah. So this is Pascal's approach. Fermat's approach is a bit different because Fermat looks at what is going to, what are the possibilities at the end, in a way. Yeah? So he says, I have 2, 0, 1, 1, 1, 1, and 0, 2, and I will attach probabilities to each of these. This is how we now see it. Of course, he doesn't use that language, but this is how we now see it. So he has probability P squared, PQ, QP, and Q squared, and then he does the same argument. He takes the expectation for this one and says it has to be equal to this one, and of course they find the same result. It is the same result, but it's fundamentally, the approach is fundamentally different, I think. Because what Fermat does is Fermat looks at the sample space in current language. Fermat has a sample space, he constructs a space of all that could happen, and he attaches a probability to everything that can happen. So he has a picture of everything that can happen in his mind and attaches probabilities to that. So he has a probability measure on a sample space. He then has an expectation and he uses that. Pascal never does that. Pascal has no idea what's happening in terms. He just uses local information and uses a local assessments that he has to come to a problem. So the difference between Pascal and Fermat, I think, is an important difference, is the difference between going local and going global. And I think that this exposes, I think, a rift between 2 ways of looking at probability that has been present from the beginning of probability theory and is still going on to this day. I think that it's fair to say that Fermat's approach has won out. We tend to work with probabilities on sample spaces. We tend to enumerate everything that can happen and then construct a probability measure on that and use that approach. We very rarely use the local approach. In some cases we do. And some aspects of probability, of current probability theory, are locally inspired, but I think the main stress has always been on the global approach. So that is one thing that I want to talk about. Another thing that I want to talk about is this forecasting idea. This beautiful idea that I have something uncertain on the right-hand side and something on the left-hand side that is supposed to have to be equivalent to this. Yeah, so I have an uncertain reward on the right-hand side, and I'm going to replace it with something that is fixed on the left-hand side. And this is an idea that I think was first printed, at least, in this 1660 book, not 1666, because that is the Fire of London, I think, but the 1660 book, Van Rekening en Spelen van Geluk, that was published by Christian Huygens. And I've given you two excerpts from that book. What I wanted to point out is there is two sentences here that are quite important. The one is even zoveel weert als. I'm going to explain that. It's not that different for someone who speaks English. Het is meer weert. It's worth to me. Yeah. So what he's saying is that this thing is worth to him this. Right. So this basic idea of I have something that is uncertain, and I'm going to replace it by something that is certain but is worth as much as the uncertain thing is present in this book. And of course, I think this is one of the basic ideas behind what Teddy's been calling coherence one, the Finetti approach to betting. So this idea, I think, was first put forward by Pascal and subsequently by Huygens in print. I think it's fair to say that. So this brings me to forecasting. And I'm going to now start to talk about forecasting of a single outcome. And later on, I'm going to make things more complicated because I want to get to randomness, and that will imply having to deal with many outcomes. But let's start by the simple things and go look at a single outcome first. Okay, I have a forecast P for something that is uncertain and that assumes values in 0 and 1. So the same plot, the same figure as before. I have 1 with a probability P, or a forecast P if you want, 1 minus P for the forecast 0. And then if I calculate the expectation of this thing trivially, what I get is P times 1 plus 1 minus P times 0, so I get P. So my forecast here on the left-hand side is precisely the probability for a while. So this P is the expectation also. It's the fair price for or the thing that is equivalent to the random reward that I get. Going to make this a bit more complicated by looking at gambles on this uncertain thing X here. So if I have a gamble on X, X can take two values. So the gamble is completely characterized by the value it has in 1, which I denote here, and the value it has in 0, which I put here. So this G, this any gamble G of X can be represented by a point in the plane. And I'm going to use figures like this quite often. So this is this function. Now, if I do the same thing, I have the value f of 1 here and f of 0 here. P times f of 1 plus 1 minus p times f of 0 gives me the expectation here. So this means that this expectation is the thing that is equivalent to the random thing on the right-hand side. Okay, if I plot for any gamble f, so any point in the square, if I look at the line for which the expectation is 0. So this is the blue line points for which the expectation is 0. So, and then I have the white region, and in the white region the expectation is positive, and in the blue shaded region the expectation is strictly negative. Okay. So what does this mean for the forecaster? As an implication of his forecast, it tells me that there are certain gambles for which his price is positive, and those gambles, since they are equivalent to something positive, he's not going to be willing to give them away, because you're not going to give something away that is strictly positive. That is not really rational. The blue gambles here in the blue zone, on the other hand, are gambles that have a price that is negative, and therefore he will willingly give them away. So as a result of his forecast P here, there is this entire region of gambles that he will be offering to other people willingly, because his price for them is negative. So remember, the blue zone is the gambles, is the region of the gambles that the forecaster is willing to give away as a result of his forecast. So to offer to other people. Okay, now let's go to interval forecasts instead of precise forecasts. There's a number of ways to do that. I'm going to try to explain how to do or how to deal with this using one particular way. They're all equivalent, but I'm going to use one way which makes it, which I think is easiest to understand in a short stretch of time. So I'm having an interval forecast with a lower bound and an upper bound, P lower and P upper. So this is the forecast here for the 1. The corresponding forecast, imprecise forecast for the 0 is then 1 minus the upper, 1 minus the lower. And so you can interpret this as a range of precise forecasts. And for each precise forecast in that interval, I have a corresponding expectation. And as my precise forecast ranges over the interval, my expectation will also range over an interval. And the lower bound for that interval is the lower expectation, and the upper bound is the upper expectation. So this means that if I give an interval forecast, I come up with an expectation interval on the left-hand side. Now, what is the region of the gambles that, as a result of the imprecise forecast, the forecaster will be willing to offer to other people, will be willing to give away? But of course, the ones for which, for every forecast, precise forecast in the interval, the corresponding price is negative. In that case, in other words, if the upper expectation is non-positive, then it's guaranteed that for all the precise forecasts in the interval, the expectation will be negative, and therefore he will definitely will be giving away those, or wants to give away those gambles, and they are the gambles in the blue region here. So in this case, gambles that are being offered as a result of this imprecise forecast constitute this blue convex cone. It's no longer a semi-plane in this case. It's a convex cone. It's a smaller cone of gambles in this case. So keep this in mind. Again, as a result of an imprecise forecast or of a forecast in general, there's a region of gambles that are being offered to other people for that, precisely as a result of the interpretation of the gamble as a price, or of the forecast as a price. Okay. This was one forecast. Now we go to many of them. So you have to imagine that you have one forecast and another, one gamble, one variable, 0 and 1, another variable, 0, 1, another variable, 0 and 1, an infinite sequence of them, of variables that may assume the values 0 and 1. Now, how can we represent those graphically in a tree? So the idea now is that the first variable is either 0 and 1. So I just draw these two lines here, and then in each of these, I have two possibilities, 0 and 1. Again, this is the value of the second variable, the value of the third variable, and so on. So what I get is a tree, and each of the nodes in the tree represents a finite sequence of zeros and ones. And these are in fact the values of the variables that have already been observed. Yeah? And I will call these nodes, I will call them situations. So situation is just a sequence of zeros and ones, a finite one, and they correspond to what has already been observed. An infinite sequence of 0 and 1s is then an infinite path in this infinite tree. So it's just an infinite sequence of zeros and ones. And of course, you can, and I will call the set of all these infinite sequences of zeros and ones, that is the sample space in this tree. And I will call the set omega, but in fact, the set of paths, a path is such an infinite sequence. This set of paths corresponds to the unit interval, right? Because every sequence of zeros and ones corresponds to a number. It's the binary expansion of a number in the unit interval. So this omega, I could equally well have written the unit interval. So that is the sample space for this tree, is the unit interval, the set of all real numbers between 0 and 1. The reason I stress the fact that we have a sample space is because I'll be coming back to the Fermat approach and the Laplace approach. Okay, I have this now. Now, I want to discuss or want to come to a notion of randomness. When is a path of 0 and 1s, an infinite sequence of 0s and 1s, when can I consider this path to be random? Now, for that, I need assessments. Right? So let's assume that we are dealing with fair coin randomness. What I'm going to do is in each of the situations in my tree, or to each of the situations in my tree, I'm going to attach an assessment, a probability of heads, or a probability of tails, if you want, if I'm flipping a coin, or 0s and 1s, in each situation. So imagine that after having observed 0 and 1s, or in other words, tails and heads, I'm just going to, based on this information, trying to guess, give a forecast for what the next outcome will be. And that forecast is in each case 1/2. So this represents fair coins. This represents independence. I'm not learning from my observations. I'm using the same 1/2 everywhere. So this is a fair coin tree. But the idea already here that we'll come back later is the idea of a forecasting system. So a forecasting system is something that maps situations to forecasts. In this case, elements or probabilities. So in this case, it just gives the same forecast 1/2 to each of the possible situations. That will become more general later on. Okay. Now, when is then a sequence of 0s and 1s random on this approach? Well, people have been thinking for this for quite a long time, and there were many suggestions until at some point a fairly reasonable suggestion was made by Martingales, and he used what we call now, or what I would call now, a global approach for determining whether a sequence of 0s and 1s is random. And the idea on which that is based is, in fact, looking at the statistical laws. So you have, for instance, the law of large numbers. The law of large numbers says that if I look at a finite sequence of 0s and 1s, so the first n, if I have my path that is an infinite sequence, I look at the first n of them, and I look at the running average over those n sequences of the outcomes, then the law of large numbers says that that running average will approach or will get close to 1/2 with higher and higher probability as soon as the sequence becomes longer and longer and longer. So that is what the law of large numbers says. So that idea leads to the idea that if a path does not satisfy, is not close enough to 1/2 at a certain time, it will violate randomness, because the random paths are the ones that are supposed to satisfy all these statistical laws. So if a path is not random, if it's not close enough to 1/2, the law will be violated. And therefore, what we get is sets that are called, you could call them exception sets. So if my path gets in a set like this, at some stage, for some length of sequence, I'm too far away from 1/2. And that's when I get into an exception set. And of course, the idea that exceptions become rarer and rarer probabilistically is modeled by the fact that the probability of these exception sets as n goes to infinity becomes exceedingly small. And so a path is random when it's not in any exception set that corresponds to this law of large numbers. So in other words, if it's not in any of the exception sets, then it will succeed this randomness test, the one that is associated with the law of large numbers. But there are many other randomness tests, and the idea there is, and this was Martingales' idea, that every randomness test corresponds to such a sequence of sets, Gn, that satisfies this thing, and then a path is random if it succeeds all randomness tests. So the idea of the law of large numbers is somehow abstractified in sequences of sets that satisfy this condition, and the idea is that they have to constitute, that they have to be in some way computable. I'm not going to go into the details of computability, but I can't have just any sequence because that would be, there would be too many of them. But I'm going to restrict the possible randomness tests to a countable number of things that are sufficiently computable. So that is, admittedly, I think, a very complicated idea. It's an elegant idea, but it's quite complicated. And it's complicated, I think, because the approach is global. So can we do a local approach? To do the local approach, to use the Pascal approach, what we do remember is we have a probability tree, and in each of the nodes, our forecaster has given a probability of 1/2. I'm going to draw the space of acceptable, the space of the gambles that forecaster, because of his forecast of 1/2, makes available. It's just everything that is below this blue line. And this is the case in every situation. Now imagine that there is a skeptic who wants to exploit forecasters for the forecast. He wants to take forecaster up on his forecast. So what he will do is he can select in each of the situations, he can select an available gamble, the gamble that is made available by forecaster because of the forecast that he's made. So that is what I will define to be a strategy. A strategy is just a function that associates with each of the situations, chooses a gamble that is available. Now, if I have such a strategy, then I can build up capital in this tree. I start with an initial capital here, and I choose a gamble in here. So let's say this gamble here, I choose it, and then if I go here, I have to take the value in 1, and that is positive. So I'm going to add the value that I get in 1 to the capital that I have here to get to the capital that I have here. Same here, if the outcome is 0, the capital was negative, so I'm going to subtract that amount to get to the capital that I have. And of course, I can repeat this in every, because I choose a gamble in every situation. I can repeat this and just flood my entire tree with capital, just starting from my strategy and from an initial capital. Just all my tree has, in a way, been flooded with capital. Okay, so that's, you have to remember that if I choose a strategy, I get what we call a capital process, so a capital in each of the situations. And this idea was then exploited by this guy, Jean Ville, in the late 1930s, early 1940s, in his thesis. So the idea of that capital process that is what we call a super martingale. So it's a capital process that is associated with a strategy. Now, when is a path random? According to this definition, when there is no strategy for which, if I go along the path and I look at the capital that is accumulated by that strategy along that path, if that does not become unbounded. Now, there are two restrictions there. The first one is that your capital can never be negative, which makes sure that skeptic is not borrowing any money. So borrowing is not allowed. So that is one thing. So it can never be negative. And there's another restriction, and that is that the capital or strategy should be, again, computable in some way. If it's not computable, then it won't work. So those are the restrictions. So the idea is a path is random if nobody, if a skeptic cannot exploit the forecaster's forecasts in order to become unboundedly rich on that path by betting on the sequence zeros and ones that are in that. That is the idea. And to me, that is a calibration idea rather than a frequentist idea. It is about forecasters' forecasts being well calibrated in such a way that he is not, people cannot exploit his forecasts in order to become infinitely rich, and therefore make him infinitely poor. So randomness in this sense is forecasting, and this type of randomness, or this approach to randomness, again, is very close to Pascal's approach and also to Huygens' approach, and the coherence one aspect of probabilities and prices. So this is being well calibrated of a forecast on the coherence one approach, because you exploit the fact that there are prices, there are things that are willing to be paid. Yeah. Right, let's go further. Question is, we have a global approach, we have a local approach. In the Pascal and Fermat correspondence, these were equivalent. Are they equivalent here? Yes, because these two guys in the 1970s proved that the local and global approaches to randomness are in fact equivalent to each other. You see that these are pictures from the 1970s. They look very 1970 like. It's Peter Schnorr and Louis Levin who proved the equivalence of these approaches. Okay, this was precise, 1/2, fair coin tree. Can we go to interval forecasts? Can we have randomness associated with intervals rather than precise numbers? Can we have imprecise randomness? Well, just to recapitulate, I think that randomness is about an outcome sequence and the forecast sequence being well calibrated. I have a sequence of outcomes, I have a sequence of forecasts, and these must go well together, or go together well. And so this idea I'm now going to try to exploit. The idea is, again, I'm going to repeat it because I think it's an important one. I have a forecaster, and in each situation, he emits a forecast, which in a way represents commitments to bet on the outcome that is going to happen after the situation. And then there's a skeptic who can take up forecaster on these forecasts and try to become very, very rich by doing that. And randomness means that this is impossible, essentially. So a path is random if on that path this cannot be done. While not borrowing, that is important, you cannot borrow money, the strategy there must be computed. So those are the two requirements. You're not allowed to borrow, and your strategy must be in some weak way computed. Okay. In precise case, once we have this, then doing imprecision in forecasting and in randomness becomes fairly easy. We have a probability tree. What we're going to do in each situation, we're going to allow for an interval forecast rather than a precise forecast. So we have a forecasting system that associates intervals with each situation. The idea being that with each interval, a forecaster offers a number of gambles in the blue region to anybody because of his interpretation of his forecast, of his forecast. He has an interval forecast, and with this there corresponds this blue region of gambles. So as before, a strategy will now be a way of selecting a gamble from these allowable regions, from these regions that that forecaster is offering in each situation. So that is a strategy. I pick in each situation, I pick one of the gambles that is offered to me by forecast. And then what randomness will mean is very simply, so I again have a super martingale. By doing that, I can flood my tree with capital, and so I get a capital process, and then a path will be random. Again, same argument, word for word, the same thing. The only thing that is different now is that in each situation, the gambles that are available are somewhat different, are somewhat more limited. So there's fewer gambles in general available than in the precise case, but the definition is fairly similar. So this is based on work that Jasper and I have done on this. We have a recent paper that has been published on this idea. Now, this is the local approach. Is there also a global approach? And this is work in progress. So things that we're looking at now that we're having some positive results for. It turns out that the local and global approaches are also here equivalent. Not going to say too much about it, but you can also have an upper probability on the sample space, and using that upper probability, get to a definition or an approach that is more or less equivalent or similar to the one that Martin gave. So here too, global and local turn out to be equivalent to each other. What is so interesting about this interval or imprecise randomness? A few results. I'm just going to list them and go through them. First one is a very cute result. I think that If I have a forecasting system, and I look at all the paths, all the sequences of zeros and ones that are random for that forecasting system, I get a set of random paths, or random numbers if you want. That set has lower probability 1, which means that almost all, in a measure theoretic sense, almost all the paths are random. So that means that if you look at this in terms of calibration, so the random sequences are the ones that are well calibrated, right? Or for which the forecasting system is well calibrated. So in other words, the forecasting system is well calibrated for almost all the sequences, which means that every forecaster thinks of himself as well calibrated. Yeah. So according to any fellow forecaster, almost all the sequences that there are will be well calibrated. This is the imprecise version of a result that Philip David proved for the precise Bayesian. So it's called the well-calibrated Bayesian. Every Bayesian is well-calibrated. Same holds, of course, for the imprecise Bayesians. They also believe themselves to be well-calibrated. Another result is like a law of large numbers. Now this one I formulated for a particular case, but it can be formulated in a much more general way as well. So what do we have? Let's look at a forecast that is constant. So I have a forecasting system that gives you the same forecast in each situation. And that forecast can be an interval, or it can be, as before, fair coin, 1/2. But let's allow it to be an interval. So it's the same interval, I, in each situation. I call that a constant or a stationary forecast. So look at any path that is random for that forecasting system. So look at a path. And along that path, we're going to take the running average of all the zeros and the ones along that path. In the precise case, that will converge to 1/2 along such a path. Here, we no longer have convergence, but we do have that the running averages form a sequence, and that sequence has a limit inferior that must dominate the lower bound of the interval, and they have a sequence whose limit superior must be dominated by the upper bound of the interval. When the interval becomes a point, the limit inferior and superior coincide, and I get to the limit result again. But this is the imprecise version of the law of large numbers, in a way, for random numbers. This complication, extra complication here is the selection process. So you can select in a computable way ones, and you can take out from that running average in a computable way things, and it doesn't affect the result. So if I just select from that sequence a subsequence in a computable way, it will still make sure that, or it will still be guaranteed that these results lie inside this interval. Okay. Maybe a few more things to be said about why we believe that we've hit upon something extraordinary by looking at imprecise randomness. Suppose that something is random for a certain interval. What happens is, I'm going to look at constant forecasts now. So I have something that is random for a certain interval. Let's look at it this way. So this means that to me it's a bit different, but to you, I think the available gambles look a bit like this, right? So that is the cone of available gambles. That would be the cone of available gambles if it were precise. If it's imprecise, it's going to go like this. It's going to become. So now let's assume that I have something like this. This is my first interval. I have something that is random for this interval, and then I'm going to look at a wider interval. Now, a wider interval means a smaller cone. Yeah? So this means that if my forecaster has this smaller cone, he will have fewer gambles that he gives to other people. Yeah? So fewer gambles will be available, which means that my skeptic will have fewer gambles to use in order to become infinitely rich. So it will become more difficult for him to become infinitely rich or unboundedly rich, which means that more sequences will be random, because the constraints on the sequence will be fewer. So larger intervals means more random sequences. If a sequence is random for a given interval, it will also be random for all super intervals, supersets. So that's one thing. That is okay. But what about the other way? If the sequence is random for an interval, will it be random for a smaller interval? Will there be smaller intervals for it that it is random for? And another question that you could think is, okay, to me, all that is important about randomness is represented by precise forecasts. So I think, or I would like to think, that this newfangled notion of randomness with respect to intervals is a bit silly, and I would suspect that everything that is random with respect to an interval will ultimately also be random with respect to a precise forecast. Not so. This is what this theorem says. There are, take a stationary forecast, an interval forecast, then there will always be paths that are random for this interval forecast, but never for any computable thing that is more precise. So this is why I think that you can say that this randomness is inherently imprecise in the sense that it doesn't go away or is not reducible to precise randomness. There's something more to it. Okay, the other one I'm not really going to talk about because I don't have a lot of time left. So this is why I think that this interval randomness is interesting and also useful. Now let me go to scoring. So these are the more half-baked ideas that I want to throw at you. So I have a scoring, and let's start with scoring a precise forecast. I have this uncertain thing x, and I have a precise forecast for it, and then this s of x and p is the score that I'm going to give for the precise forecast of this uncertain outcome x. And the idea behind the score is that the higher the score, the better the precise forecast is. Whatever better may mean, right? Doesn't really mean much if you don't say what better is. So there's ways of trying to restrict what better means by imposing propriety rules. So this is the properness that that Teddy was discussing yesterday. The idea is that the scoring rule will be proper if the expectation, if somebody has a probability or a forecast P, then this expectation of the difference between the score for this forecast and any other forecast will be positive. So his own forecast will be the best, or his own will have the highest score. That is the propriety rule, the properness rule. And then there's this little theorem that is inspired by Phil Davis' work that says that take a precise forecasting system that is computed. Take two of them, a phi and a psi. And assume that I have a path that is random, so well calibrated, so for phi. So phi is well calibrated for that path. Well calibrated in the sense of coherence 1, right? It's about prices and becoming infinitely rich. So it's about, in the sense of avoiding a sure loss, or an infinite sure loss, if you want. So that is well calibrated in that sense. Then it's also going to be well calibrated in the scoring sense. In what sense? Look at the score that you get along the sequence. So omega sub k is just the outcome of the sequence at position k, and this is the score for that according to the forecasting. The forecast for that according to the forecasting system. And so this is the score for betting on omegas at position k using the forecasting system phi. And here is the score for betting on that same using the forecasting system psi. Then the difference between these two is what I can locally gain by using the phi forecast as opposed to the psi one. And I'm going to take the running average of those. And then you can prove that the limit inferior of that running average is non-negative along the random sequence. So in other words, this tells me that if I have a forecasting system that is well calibrated in the sense of coherence 1, or to a certain sequence, then it will also be, if the proper rule is, the scoring rule is proper, it will also be, in this sense, have nice properties for, in the sense of coherence number 2. That is in the precise case. So now we go to the imprecise case. I'm going to have, or consider, an interval forecast and use the same thing, score. I have an uncertain outcome, I have an interval forecast, and I'm going to use the scoring rule to attach a score to that forecast for a given outcome. And again, the idea would be that the higher the score, the better the interval forecast will be. Again, whatever better may mean, we can now try to impose a number of properness rules or properness properties for such a scoring rule. First one, I'm just making suggestions, right? I'm not suggesting that this is the right way to define properness. It's not, but I'm just trying to suggest, because kicking ideas around. Okay, what I'm going to do is I'm going to start with the property that we had before, the properness property that we had before. And I'm just going to change the expectation that I have there by into a lower expectation, which is very strong, of course. Yeah? A very strong word. Now, it's very strong, but it has a nice consequence that turns this again into a theorem. This becomes a theorem. You can prove using what we did in our paper, that if you have a computable forecasting system, it needn't be precise, so it will be imprecise in this case. If you have a computable forecasting system, and we have a proper scoring rule S in this sense, then we will have the same theorem. So take a path that is random, that is well calibrated. So in other words, such that the forecasting system phi is well calibrated for that path, then it will have the same property for the difference between the scores on that path. Okay, that seems nice. The only thing is that this is far too strong. This implies, for instance, that the score of an imprecise of the vacuous will dominate the score of all the other ones. So it will. This is a score that in some way will favor being vacuous. Yeah. So, or perhaps not what you want for all aspects of. So this would seem to favor being as conservative as possible. But it does this at least. Okay, let's try and make it a bit weaker then. So call a scoring rule proper if this, so where we replace the lower expectation by an upper expectation. So it becomes quite a lot weaker, I think. This is what you would do if you wanted to express that the interval I is undominated under the maximality condition by any other interval, by any other forecast, any other interval forecast. That is what you would do according to maximality. Then, and I very strongly doubt that this will then be a theorem, because that is far too weak in this case. So this is, it seems nicer, but it will not probably not make that work. So, okay, other suggestion. Let's, instead of going to maximality, go to admissibility. So use this condition. Switch the contours. Okay, then I'm not sure. I haven't really thought about this because I was only thinking about this in writing down the slides, but I have a slight suspicion that we might be able to do something with this. We might be able to prove something like this. Not sure, but what I'm actually saying is that this might be an interesting. So what I'm trying to say, perhaps, having given all these suggestions, is that since there seems to be this connection between being well calibrated on the coherence 1 approach, and then this property, which suggests a way of being calibrated on the coherence 2 approach, associated with infinite sequences, it might be a good idea to start investigating possible properties of properness and check whether they satisfy this condition as well. They can prove something like this as well. So this might be something as a research suggestion that that might make sense. Perhaps somebody will tell me it doesn't make sense because of this and this and this. It's perfectly fine. It's not my problem, the scoring problem. But this is what I would suggest looking at or looking into. That is all I wanted to say. And I'd be very happy to answer any questions or problems that you might have.